Hey everyone, and welcome to The Explainer. I am absolutely thrilled to have you here today because we are going to be decoding the visual magic behind algebraic identities. If you've ever stared at a really complex math problem and thought, man, there has to be a faster way to do this, well, you are exactly in the right place. Whether you're a student prepping for advanced math or just someone looking to sharpen up that mental toolkit, today is going to be fun. We're not just going to blindly memorize formulas. No way! We're going to see them, we're going to physically build them, and then we're going to use them to slice through complicated math like a hot knife through butter. Let's get started.
All right, jumping right into Section 1, the magic of number patterns. Math is fundamentally just the study of patterns. So to get our brains fired up, let's look at a pretty wild one hiding right under our noses.
I want you to consider 3 consecutive square numbers. Let's start with the absolute simplest ones, 1, 4, and 9. Now, what actually happens if we decide to play around with these numbers using a very specific set of rules? Let's take a look.
Check out this first puzzle, our first solved question for the day. Step 1, we take the smallest square, which is 1, and the largest square, 9, and we just add them together to get 10. Simple enough. Step 2, we take that sum, and we subtract exactly twice the middle square. Well, the middle square is 4. Twice that is 8. Step 3, 10 minus 8 gives us a result of 2. Now, you're probably thinking, okay, a fun little coincidence, whatever, but try with the consecutive squares 25, 36, and 49. 25 plus 49 is 74. Subtract twice 36, which is 72, and boom, you get 2 again. It miraculously equals 2 every single time.
Moving right along to Section 2, equations versus identities. That pattern is incredible, right? But I promise you, it isn't magic. It's actually just structural perfection. Which brings us to understanding the core difference between your standard equations and algebraic identities.
Let's define exactly what we're dealing with here. An algebraic identity is a special kind of equation. The absolutely crucial point to remember is that it is true for all values of the variables inside it. It's not a temporary condition, it's a universal mathematical rule. It's a structural truth of numbers themselves.
And this slide brilliantly illustrates the difference. Look at the left side for a second. We have a standard equation. X squared minus 1 equals 24. Now, this is only true if x is exactly 5 or negative 5. It's kind of like a lock that only accepts 2 very specific keys. But look over at the right side, the identity. X plus y squared equals x squared plus 2xy plus y squared. This is true for literally any numbers you decide to plug into x and y. It's not a puzzle where you have to find a missing number, it's a literal blueprint of how numbers behave.
Okay, Section 3, visualizing math with shapes. Let's move away from abstract letters for a second and look at why this actually works in the real physical world.
This is where algebra turns into geometry, and it's so cool. Imagine a line segment of length A connected to a line segment of length B. If we build a physical square out of that new, longer A plus B side, the total area is going to be A plus B squared. But look at how that area naturally breaks down inside those colored boxes. You physically get one large square with area A squared, a smaller square with area B squared, and 2 identical rectangles, each with an area of A times B. Add them all up, A squared plus 2AB plus B squared. It perfectly matches. It physically has to be true. And honestly, this completely clears up that common confusion where students mistakenly think A plus B squared is just A squared plus B squared. You absolutely cannot forget those 2 extra rectangles.
Which leads us perfectly into Section 4, proving the universal rule. So we can clearly see the physical geometry, but does this rule hold up for numbers that can't be physical lengths?
Let's tackle solved question 2 to find out. Let's force our variables into the negatives, where drawing a physical square is impossible. Let A equal -2 and B equal -3. If we use the left side of our identity, A plus B is -5, and -5 squared is 25. Now let's use the expanded right side. A squared is 4, B squared is 9, and 2 times A times B is 12. Add them up. 4 plus 12 plus 9 equals 25. So even though we literally can't draw a square with a negative length, the structural identity holds flawlessly.
Oh, and just a quick side note, this mathematical perfection absolutely applies to fractions and rational numbers too. If you try this with A as -2/3 and B as 3/4, both sides of the identity will beautifully, perfectly calculate out to 1 over 144. No exceptions.
And the reason this works across all number types is cemented by the distributive property. As you can see right here, if you multiply the binomial A plus B by itself, you distribute the A to both terms, then you distribute the B to both terms, and finally you combine the results. This essentially proves our universal rule mathematically, completely backing up what we just proved visually with the shapes.
All right, Section 5, solving complex problems faster. Now let's unleash these identities as powerful, real-world shortcuts for advanced calculations.
Here is solved question 3. I want you to imagine you are sitting in an exam, or maybe you're estimating materials for an engineering project, and you suddenly need to square the number 119, but you don't have a calculator. 119 times 119 by hand? That's tedious, it takes forever, and it's super prone to errors. But what if we use our structural knowledge? We can just rewrite 119 as 100 plus 10 plus 9. Suddenly, we can apply an expanded version of our identity, the square of a plus b plus c. We just square each part. 100 squared is 10,000, 10 squared is 100, 9 squared is 81. Easy. Then we add twice the products of each pair. Twice 100 times 10 is 2,000. Twice 100 times 9 is 1,800. Twice 10 times 9 is 180. Add those simple round numbers together, you can even do it in your head, and you effortlessly arrive at 14,161. That is the real power of identities. They turn hard multiplication into super simple addition.
Now we can also run this whole process in reverse, which brings us to solved question 4. If an identity lets us expand things out, it also lets us collapse or factor expressions back down. Take a look at these visual algebra tiles representing the expression x squared plus 7x plus 12. By just arranging one giant x squared tile, 7 single x tiles, and 12 one-unit tiles into a perfect rectangle, we can instantly see the side lengths. The sides are exactly x plus 3 and x plus 4. Bam! We've just factored a quadratic equation visually.
Which prepares us perfectly for solved question 5. Take a look at this absolute unit of a rational expression. For a lot of students, seeing a fraction with polynomials on the top and bottom causes instant, total panic. Like, how do you even begin to simplify this monster?
Well, you use identities. Let's tackle the top first. X squared minus 7x plus 12. We just need two numbers that add up to -7 but multiply to positive 12. Those numbers are -3 and -4. So the top simply becomes the clean little linear blocks of x minus 3 times x minus 4. You do that exact same factorization for the bottom using an identity. Find the common factor and just cancel it right out. What looks like an absolute nightmare simplifies down into a clean, elegant fraction with total ease.
And hey, this logical pattern doesn't stop at flat 2D squares either. It extends right into three-dimensional shapes and complex binomials. If we cube an expression, like a plus b to the third power, it's really just the volume of a giant cube sliced into smaller cubes and cuboids. The identity perfectly expands into a cubed plus 3a squared b plus 3ab squared plus b cubed. The underlying structure is literally everywhere once you know how to look for it.
Okay, Section 6, test your math skills. We've covered a ton of ground today, and now it's time to put you in the driver's seat.
Here is a challenging practice question straight out of the advanced concepts we've been touching on today. If you know that a plus b plus c equals 5, and the sum of their cross products is 10, can you find the exact numerical value of this massive expression? A cubed plus b cubed plus c cubed minus 3abc. At first glance, it looks completely impossible, but if you map out the right identity, it will collapse into a shockingly simple answer. Grab a screenshot of this slide and definitely try to solve it later.
And I'm going to leave you with this final thought and a little debate to chew on. James and Reshma are looking at the exact same expression, the square of a minus b multiplied by a plus b. James decides to expand the squared term first to get a long polynomial to multiply out, but Reshma pulls one a minus b out, pairs it with the a plus b to create an a squared minus b squared identity, and multiplies that by the remaining a minus b. So, who has mathematically applied the identities correctly here? Are they both right? Which way is actually faster? I really want you to think about those underlying structures of numbers we've explored today. Thank you so much for joining me on this explainer. Keep looking for those hidden math shortcuts, and I'll catch you next time.